Last page, we're going to use our inverse trig functions to find angles within right triangles. This was the whole reason why we restricted our output values to include first quadrant. We always wanted a value between 0 and 90 because we want to use it for right triangles. I'm not going to do every single one. I'll probably go down the left-hand side of the page. We were trying to find this acute angle. We have 90 degrees and this acute angle. What do we know? We know 4 and 9. 9 is a hypotenuse, 4 is the adjacent side. What inverse trig function do we want to use that uses a ratio of 9 and 4? Well, I think cosine would be the appropriate thing to do because the cosine of theta is 4/9. Let's use the cosine inverse. So second cosine, 4/9. We're going to input a ratio. We're going to output an angle of 63.6 degrees. We want to round to the nearest tenth as the directions say. So theta is approximately 63.6 degrees. We can then unlock all the rest of the angles and the other sides by doing other things like Pythagorean theorem and then the triangle sum theorem, but we're not about that. Not right now. Let's do letter C. Here we have an angle. We have 12 and 5. 5 is adjacent, 12 is opposite. So that means the tangent of theta is opposite over adjacent 12/5. Let's find the tangent inverse of 12/5 to give us the value of that angle. So this is really the whole reason for today. I didn't mention it yet, but the reason you want to use these inverse trig functions is given a ratio, you want to find the angle. This pretty much summarizes why we are doing what we're doing today. Looks like the theta value is approximately 67.4 degrees. The 8 rounds the 3 up to another tenth. All right, let's take a look at this last one, letter E. Now, we only can use these trig ratios when we have right triangles. I don't think if I did Pythagorean theorem, this would work out because the long side should be the hypotenuse, and we can't have two sides that are the longest side. That kind of contradicts itself. But what I do notice is that both of these measures are 15, and one of the other sides is 12. So what happens when we have two side lengths in a triangle that are the same, at least two? We have an isosceles triangle. Now, that would just mean that the base angles are the same. I'm still not sure how I'm going to use some inverse trig because I don't have right triangles. What I think we could do is, let's do the best we can to split this picture down the middle, perpendicular to the base. We're going to call that the base because, you know, these are called base angles. That makes sense. And draw a perpendicular, an altitude up from the base to the vertex at the top. This now splits this angle in two. So finding this theta, I'm just going to call this like theta 2 in order to find theta 1. We're going to double this to get the angle for the full theta, which means this side length isn't 12 anymore, and this right triangle at the right, it would be a 6. So we have the opposite and the hypotenuse, 6/15. So the sine of theta sub 2 is 6/15. I don't need to simplify this fraction because it's part of my work. So let's do the sine inverse of 6/15. My calculator can do that for me. I don't need to simplify it. Gives me 23.578, etc. I don't need to simplify this. I also don't need to round this answer. I want to round the answer that is at the end of my last step. The last step I want to do is round. So what I want to do is, before I round it, let's double this angle. Doubling it is going to give us both sides of this altitude. Doubling it gives us the value of theta is approximately 47.2 degrees. So we were able to be clever with this last one. There are a couple more that we could do, but I'm going to stop here so you have enough time to start your homework. Good luck to you. If you have any questions, please feel free to reach out to me. Thank you.